My talk today is based on a joint work with Kolya Bogachev, Leonid Slavich, and Sasha Kolpakov. The names will appear later during the talk. And I'm going to talk about subspace stabilizers in hyperbolic lattices. Well, first, what is the object of the talk? So we look at the quotient of hyperbolic n-dimensional space by a finite covolume lattice, gamma. So this gives us what we call a hyperbolic orbifold. Everybody knows in the audience about these objects. And then we look at totally geodesically immersed suborbifolds of M. So subspaces of smaller dimension, this with the same curvature conditions, and okay, they are also quotients of hyperbolic smaller dimensional space by some lattices. Well, first of all, let me recall an important breakthrough proved by several years ago by Margulis and Mohammadi in dimension 3 and Bader, Fisher, Miller, Stover in general. So they showed that if M, this orbifold, contains infinitely many maximal totally geodesic subspaces of dimension at least 2. So in dimension 3, what Margulis and Mohammadi proves that if M contains infinitely many totally geodesic surfaces, then M has to be arithmetic. So this was a long time an open question or conjecture. It was first asked informally by Alan Reed, and then also appeared later in papers by McMullen. So the problem was well known and the conjecture was clear. However, the proof is difficult and it uses new superrigidity theorem, actually different theorems which were proved by first authors and second group of authors independently. Now, observe that arithmetic hyperbolic 3 orbifolds or manifolds which are not of the simplest type, so not defined by quadratic forms, are excluded from this theorem a priori because there is a previous known result by McLachlan and Reed which said that arithmetic hyperbolic 3 orbifold has totally geodesic surface codimension 1 suborbifold if and only if it's of the simplest type. It's defined by quadratic form. So, well, the other kind of downside of this result and the method used is that it tells very little, if nothing, about the nature of these totally geodesic surfaces because, okay, they come from ergodic arguments, so you can say something maybe, but in general, you don't have control over these suborbifolds. So these two remarks, and also importantly for us, the previous study of hyperbolic reflection groups based on the work of Winberg and its further developments. So this was our motivation to ask some questions about some further questions about totally geodesic suborbifolds. And as a first step to approach these further questions, let me give you a definition of what we call FC subspace or finite centralizer subspace. So a totally geodesic suborbifold of an orbifold M will be called finite centralizer subspace if there exists a finite subgroup of commensurator of gamma such that this subspace is formed by fixed points of this subgroup when it acts on the universal cover. Well, here just to recall some definition of a fixed points are points which are fixed by isometries, and commensurator is a well-known object, and I'm sure well, it appeared already many times during the weeks of the conference. So commensuratory is the set of elements such that in the whole D group, isometry group, that commensurate the lattice gamma. So the intersection has finite index in gamma and the conjugate. Well, so this is a well-known object, and perhaps a few words about intuition about these FC subspaces. So first case would be that when we have a, say, hyperbolic manifold and a symmetry, so isometry of this manifold, which has some fixed points, so which acts with fixed points. Then it's not hard to see that this subspace of the fixed points will be a totally geodesic subspace, and this is one of the basic cases. However, it may happen, for instance, that M has no any symmetries, and then then we don't have any fixed points of that kind. However, the idea here would be that we can look at symmetries of the finite coverings of the manifold M, of any finite sheet covering, and the symmetries of that covering already allow us produce totally geodesic subspaces of M. And this is essentially what we do here. So, well, the first observation, I'm not going to prove it, but it's not, well, it requires a proof, which we give in the paper. FC subspace of positive dimension of dimension at least 2 of a finite volume hyperbolic orbifold is a finite volume hyperbolic orbifold. Dimension 1 here is excluded because, you can, if for instance your orbifold has 2 cusps, you can manage to join these cusps by infinite geodesic and make it FC subspace. So, well, it has to be excluded. But if it's dimension greater or equal than 2, then even if there are cusps, there will be some, perhaps it can be a cusp subspace, but it will be a finite one. Well, now I can talk about our first results. So the first theorem is the following dichotomy. Says that a finite volume hyperbolic orbifold is arithmetic if and only if it has infinitely many FC subspaces. So, well, as in the previous result, we are talking about totally geodesic subspaces of M. However, we somewhat restrict to subspaces of special kind, but it immediately allows us to include also 3-dimensional orbifolds and 2-dimensional surfaces. So what happens with surface? I think I will have a corollary, so let me get there. Well, more specifically, in this paper with Bogachov, Kolpakov, Slavich, we prove that if M is a finite volume orbifold of dimension greater or equal than 2, then in an arithmetic case, all the totally geodesic subspaces, so totally geodesic subspaces in the sense of the first slide, so you can recall the theorem of Margulis-Muhammadi in dimension 3. So all the subspaces of codimension at most these are FC subspaces. And in non-arithmetic case, not only we know that there are finitely many FC subspaces, we also can bound the number of these subspaces by a linear bound depending on the volume of the ambient manifold. Well, and let me show the 2 corollaries. I hope you can see both of them. So the second one appears down the screen. So the first corollary is that if we check the condition of theorem 3 for dimension 3, hyperbolic dimension 3, then we see that actually we proved that if M is arithmetic 3 orbifold, then all totally geodesic subspaces are FC. And there are infinitely many of them. So, well, to be more specific, there can be several cases here. So I will talk late during the talk about types of arithmetic hyperbolic orbifolds. And in dimension 3, there are 3 possible types. Simplest type, type 1, type 2, and type 3. Well, in type 1, it's well known that it has arithmetic, it has totally geodesic hypersurfaces. And well, and there are infinitely many of them. And they are all of these FC types. So they, in fact, there is a reflection, hyperbolic reflection, which fixes the, for each hypersurface, there is a reflection which fixes it. Now, what happens in type 2 and type 3 is that there are no any hypersurfaces. But of course, there are infinitely many geodesic lines on the space, on these hyperbolic spaces. It's well known. However, what happens is that in arithmetic case, we prove that all these geodesics are FC. So for each geodesic, there is a involution which is going to be a rotation with this axis that fixes the axis. In fact, this was also known, and it's due to Long and Reed. And in non-arithmetic case, well, there are still infinitely many geodesics by geometric arguments. However, well, what we can observe is that there are only finitely many of them which have relation to commutator of the lattice, and the rest are geometric geodesics, but they are not of this FC type. So we have a strict dichotomy, and that also kind of explains what happens with the surfaces of dimension 2. We have strict dichotomy between arithmetic and non-arithmetic case in terms of these FC subspaces. So I will say a few words about the proof of the first theorem, well, theorem 2. And the proof is based on, well, the proof is based on 2 well-known ingredients. So the first is Borel's density theorem. Here I mean the density theorem of the commutator of an arithmetic lattice. So Borel proved that many years ago that commutator of an arithmetic subgroup is dense in the ambient Lie group, and then Margulis later proved the other counterpart for non-arithmetic lattices. So, well, in that sense, for non-arithmetic case, we use again the very classical results, Margulis superrigidity theorem, to well, basically, which implies that commutator of a non-arithmetic lattice is discrete. So it's a lattice again, and for that, from that fact, we deduce that can be only finitely many these FC subspaces up to natural equivalence in non-arithmetic case. Well, in arithmetic case, in order to get advantage of Borel density theorem, well, basically what it says is that in order to see infinitely many FC subspaces in an arithmetic case, we need to construct at least one of them. So we need a one FC subspace, and then density implies that there are infinitely many in arithmetic. And for each one, to construct one, we need to find this finite order, well, finite subgroups in the commutator. What we do is we find involutions in commutator. So finite subgroups of order 2. That appears to be sufficient for the purpose of this theorem. And well, we actually classify all possible involutions in type 1 and type 2 arithmetic cases. And well, we could not quite classify all in Tralle case, which I will going to talk later on today. That is perhaps the most interesting case. But the challenge is, yeah, to find an involution which sits in commutator, and that requires detailed analysis, which is, okay, to some extent well known in type 1 and perhaps type 2, but in exceptional cases, that appear in dimension 3 and 7, that becomes very delicate, and that is construction of involutions for Tralle lattices is perhaps the main one of the main results of our paper. Well, so in order to prove theorem, let me just go back. So there was theorem 2 and theorem 3. Theorem 2 gives dichotomy without telling much about the subspaces. Theorem 3 provides more detailed information. And in order to obtain this more detailed information, and that is valuable, I believe. So in order to obtain this information, we had to develop some technical results that can be interesting by themselves. So these are the main results from technical side of our paper. Here is the first theorem. So, well, I'm going to use some more terminology. I hope it's familiar to people in the audience, but basically, okay, here quasi-arithmetic, quasi you can ignore, and just if you haven't seen it, so it's some weakening of arithmeticity that we can also control, but the theorem already up. The principal case is arithmetic hyperbolic orbifold. Now, a joint trace field is an invariant which is defined by Winberg. So he defined ambient group, which is a joint group, algebraic K group associated to an arithmetic lattice, and the field K over which this group is defined is the joint trace field. It's okay. If you are familiar with what is called field of definition, it's more or less the same with little difference in some cases. And then we look at the finite volume totally geodesic suborbifold, and it also has, okay, it's a joint trace field. And the result is that okay, the arithmeticity descend to the suborbifold, but the field of definition can become bigger, can stay the same, can also be stable, or it can be a larger field. And this observation is important for us. So first of all, it allows us to define special case when the field of a joint trace field of the suborbifold is equal to the field of the ambient orbifold. We call it subform space. Because, for instance, in the simplest type, when the orbifold M is defined by a quadratic form, then this subform space will correspond to a restriction of this quadratic form to some subspace defined over so K subspace of smaller dimension. Here are some basic properties of the subform spaces. So, well, subform spaces are always of FC type. So there is always a involution in commutator of gamma of arithmetic lattice that fixes this subform space. Also, well, the type of arithmetic lattice again appears here and will reappear more. I will say a little more about the types later during the talk, but okay, the type of the lattice is, if it's type 1 or type 2, descend to the subform space. So if you find orbifold defined by quadratic form, then any subform space, doesn't matter codimension, will be also defined by some quadratic form. Well, here is the second theorem. So, well, first of all, let me indicate that the fact that we define subform space hints that there will be some other subspaces. And so what are these other subspaces, which are not subform spaces? Well, these other subspaces is when the field of definition is bigger, straightly bigger than the field of definition of ambient default. And here is the second theorem in this set, so theorem 5 in my enumeration, that explains about the nature of these other spaces. So the principal case here is then when degree of the extension field is bigger than 1. Together with the theorem, let me give a definition. So what happens is that the other spaces, which are not some subform spaces, they are obtained using a well-known classical construction of Weyl restriction of scalars. So you can take a arithmetic group defined over a bigger field, and using restriction of scalars, you can actually restrict it down to Q and consider it as a subgroup of the I don't know, GL and Q. But we want to keep the ambient group as the group of associated to hyperbolic space. So we work inside these groups of type PO and 1, and take a little more care about the fields. But also it can happen that, and I will show examples later on, that you restrict scalars from bigger field to smaller field, and you get honest arithmetic suborbifold of ambient orbifold. And then, okay, basically you can combine these two constructions, and we can show that there is nothing else you can do. So whenever you have a totally geodetic immersion, you can always obtain it as by one-step combination of Weyl restriction of scalars and restriction of a form. So as combination of subform space and the Weyl restriction. And okay, this structure we developed it for hyperbolic orbifolds, but it's general, so it applies to arithmetic subgroups in, say, semi-simple Lie groups. We are planning to write it down because it allows a lot of control over the subspace and the ambient space. And for instance, we have information about relation between, say, codimension and the field of definition, and that can be useful in some applications. So I'm not going to talk about the proofs of the theorems. You can find them in the paper, but I would like to show a couple of examples which illustrate, I think they illustrate quite well what's happening in relation to these technical theorems. So, well, here are my couple of examples. I will not say all the details about these examples. They also come from our paper, so you can find more details there, but I will try to give enough details for those who are familiar with the subject to understand what is going on, and to others maybe to have a good idea of what we are doing. So we consider a quadratic space defined over Q. So the Q, and we take a symmetric bilinear form. Well, you can also think about quadratic form given by a block diagonal matrix. So it has one hyperbolic component, and then the complement is all diagonal you can also write it as a, okay, it will occupy more space, but you can write it as a 2, 2, 2, 2, 2, 2 diagonal matrix, and then one block anti-diagonal 0, 1, 1, 0. A very simple matrix. Then we can consider the following matrix in the same basis, which is given by okay, this kind of blocks. And well, here are a few observations which we have. So first of all, these are all easy to check by. So first of all, if you conjugate A by M, you get A. So so M is commensurates this quadratic form. We can say this. Also, M is an involution. Square is equal to 1. And finally, here is something perhaps less obvious, but also easy to check, that although, as you can see, entries of M are in the field quadratic extension of Q root 5, when you look at them, at this operation of conjugation action of M by M, it is actually given by the way it acts on coordinates is given by polynomial with coefficients in Q and not in Q root 5. So although it has entries in Q root 5, it corresponds to involution which sits in PO of Q points of the group. Well, now we are interested in the fixed points of M, how it acts. So we can consider well, it's an involution, and it has two eigenvalues. One eigenvalue, well, coming with multiplicity, but one is 1 and another is -1. So the multiplicity of 1 is n plus 1 over 2, and multiplicity is -1 is also n plus 1 over 2. And we can write the positive eigenspace in the basis and negative eigenspace same basis. So, well, believe me that it's correct. And now we can look at the restriction of this quadratic form, which we started with, on the positive and negative eigenspaces. And we check that, okay, the restriction is quadratic forms. And in the case of restriction to positive eigenspace, we have quadratic form of signature -1, say M, and in the restriction of the complementary eigenspace, we have okay, positive definite quadratic form. Well, this is all checked by computation, and here it's written. So G has signature n-1 over 2, 1, and moreover, it's if you look at its Gauss conjugate by the automorphism of the Q root 5, then it's positive definite, and okay, so it's admissible form. Well, and H was positive definite, so we can very explicitly see how the restriction of scalars from Q root 5 over Q of G sits inside the orthogonal group of the big initial quadratic form, and okay, it preserves the decomposition. And well, so this illustrates how this Weil restriction of scalars gives us, in a very concrete way, totally geodesic subspace of quite large codimension in the ambient space defined over Q. So we put this arithmetic lattice over Q root 5 in a arithmetic lattice over Q. And the first example, and as a second example, I want to discuss how, okay, again comes type 1 and type 2, and now they will come in a little more explicit way. So how an arithmetic lattice defined by quadratic form can contain as a sublattice an arithmetic lattice defined by a skew-Hermitian form over division algebra. So, well, again, it's a very explicit example which has, I will share the slides after the talk, and okay, there are some other more details in the paper. Those who are interested can go through the details. I will go a little bit faster. So we consider quaternion algebra given by this Hilbert symbol over Q. And then we take quadratic extension of Q and consider a K algebra given by extension of scalars from Q to K of this D prime, and we observe that it splits because 3 is a square in the bigger field K. Now we consider admissible quadratic form defined over this quadratic field of signature 2m minus 1, 1. So, well, it's admissible means that Galois conjugates are totally definite quadratic forms. So this quadratic form can be used to produce an type 1 arithmetic lattice in orthogonal group of signature 2m minus 1, 1. Now we can extend this form to a skew-Hermitian form on this extended algebra. And it's also admissible in the sense that it gives a form, gives again an arithmetic space. So now we consider this lattice associated to the skew-Hermitian form, but because D is a division algebra, it's not. There is a criterion somewhat well known that in this case it's type 1 lattice. However, D prime was not was what? Okay, they are all division algebra, but D prime was not split. D is split, and that's why it's a matrix algebra. So that's why it's type 1, and D prime is not split. So it's an, let's say, honest type 2 lattice. And well, what we get from this construction is that type 1 orbifold, this dimension, is contained in the type 2 orbifold of this dimension. Sorry, let me see if I showed that type 1 lattice realizes sublattice of type 2 lattice. Otherwise, other way around, it's not possible. So in type 1, all sublattice will be type 1. Well, now the last 15 minutes of the talk, I would like to talk about the most interesting case in some way. So it's also the most challenging case. So when we realized that we can do something about this 7-dimensional Tralle-Italian type, we thought that we should write a paper because that is something new and also gets us to the area that still keeps a lot of open problems. So perhaps summarizing what I mentioned already several times, when we look at the arithmetic subgroups of the groups of isometry of these real hyperbolic spaces, we encounter three types of arithmetic subgroups. First, defined by quadratic forms. Second, only in odd dimensions appears the type which can be defined by skew-Hermitian forms. And then there is in dimension 3 and in dimension 7, there are arithmetic lattices of type 3 or exceptional type. Well, you can define them as as arithmetic subgroups which are not of type 1 or type 2. But it's not very good definition. So we do consider in some details hyperbolic dimension 3. However, I will not talk about it here. In dimension 3, there are also interesting open questions about this exceptional type. For instance, from the work of Milson and Lee and Milson, it's known that if you look at type 1 or type 2 arithmetic subgroup of PSL2C, has a congruence covering with a positive first Betti number. And for type 3, it's not known. Even if you bring in the fundamental result of Agel, who solved this virtual first Betti number conjecture for all hyperbolic 3 orbitals, arithmetic or not, it will not tell you the answer to this question about congruence subgroups, because subgroups which are produced by Agel's technology or Agel-Weiss technology, they're not congruence. And it's not known if you can take a congruence subgroup which has positive first Betti number in dimension 3. Well, in dimension 7, there are even more open questions. So what are we talking about here? And why this egalitarian 7-dimensional lattices appear? Well, when we are talking about arithmetic hyperbolic orbitals in dimension 7, we consider the associated Lie group is a type D4, and if you consider it as an algebraic group, there are following Tits classification. So that is another way, actually, a better way to say why there are why there are three types of arithmetic subgroups. Well, you look at Tits classification of algebraic groups over a number field, and you say that your algebraic group is admissible if it can give you an arithmetic lattice in hyperbolic n space, and then you check carefully through Tits work which groups are admissible. And you see, well, there will be always groups of type B or D, and in hyperbolic case. And well, this classification will also give you the possible types of the arithmetic lattices. So the exceptional type appears in dimension 7, which corresponds to D4, because of the so if you look at the Dinkin diagram of this group D4, it's well known how it looks. It's like a tripod, and it has particularly large group of symmetries for so it has symmetric group S3 acting by symmetries on this Dinkin diagram, and then type of index which we are interested in is the following type. So here the whole the absolute Galois group of the base field of the field K acts as on the diagram as a whole symmetry group of the diagram S3, and then symmetries are indicated. Well, assuming all the necessary preliminary information, we can define type 3 arithmetic lattices in dimension 7 as the ones which come from this Tralle groups, algebraic K groups G of index 6G40. As you can see, this group, well, it has to be defined over K, which has positive degree over Q. So you cannot define this Tralle lattice over Q, but over quadratic extension or of any other totally real field, you can define it. What else? And also from basic properties of this definition, it follows that this Tralle space type will be always compact. So we're dealing with co-compact arithmetic lattices. Oh, then our quest was to take one of these arithmetic lattices, gamma of type 3, and okay, our problem was to find an involution in commutator of gamma. So at the end of the day, we were able to find 3 different involutions, so they are not conjugate to each other, but actually they generate a Klein 4 group. So the product of 2 of them is equal to the third one. And how we define it, we look at the action of the absolute Galois group on the root system, and then we can see partitions of the roots which are compatible with the action, and which partition of this of the 3 allows to define involution. We define it just by the action on the roots, but then we check that okay, so in a sense we define it on the level of the Lie algebra, but then we check that it gives us an involution in the algebraic in K points of G. And okay, we did not define one involution, we defined 3 different involutions. And then okay, next, what are their fixed point sets? So this will be, in our terminology, corresponding FC subspaces. And this is already quite interesting because what comes out is for each of these 3 involutions, the fixed point set will be a 3-dimensional type 3 hyperbolic arithmetic subgroup. So we have this configuration of 3-dimensional subspaces, totally geodesic, inside of a 7-dimensional subspace. Also, each different, if you one involution of one type and another involution of another type in our classification, then the corresponding subspaces will intersect in 1-dimensional geodesic. So the whole nice structure appears in, and it's quite concrete. So easy, to, at least for me, to work with this Cayley algebras and okay, the way you define 7-dimensional arithmetic type 3, but at the end of the day, we were able to track them down and see this 3-dimensional type 3 total geodesic subspace. For Rajan particularly, I can tell that. So I mentioned question about Betty number and that it's open for type 3 arithmetic 3-dimensional lattices, but it's open for some of them. But for some of them, the answer is no, that you can produce congruence covering, in particular from the work of Rajan. And we observed that work applies to our case. So that three-dimensional totally geodesic type 3 in seven dimensional type 3 that we found there. They're a little less mysterious than some others, so we can say that they have coverings with positive transbacking number. So they very recently there was another application of this construction of involutions in the work of Bogachev, Slavich, and Son. There is a short paper in archive a few months ago. They showed that all arithmetic lattices in type here. Well, in a sense, it's an intentions type. So all arithmetic lattices in P or N1 for n greater than 3 are not LERF, not locally extended residually finite. Well, actually, what they prove is that arithmetic lattices in PO71 are not LERF in that paper, and all the other cases were already known by the previous work of Son. So often people exclude from the statement, at least in this area about arithmetic hyperbolic 3 for the type 3 dimension 7 is excluded. Now we didn't prove all what so far we didn't prove all what we want to know about them, but we managed to get a little more structure inside there and make it visible and make it useful, and so it has some applications. To conclude, I have a couple of minutes. I wanted to say about some questions. There are many questions, in particular about this Tralle type 7, but before giving some questions, let me recall very beautiful theorem by Bergeron and Clazel some years ago. So they showed that congruent subgroups of Tralle lattices have vanishing first Becky numbers. So what does it mean? Well, if you look at the high rank lattice, then say you look at high rank lattice in a simple the group, then it has Kazan property T, and Kazan property T implies that it will have vanishing first Betti numbers for congruent counters. Here we are talking about type 1 lattices, which do not have property, and they normally have first Betti numbers, grow into infinity when you look at congruence coverings. This is what, for instance, Muson proved for type 1, type 2. But here, it's one of the most striking manifestations how this type 3 7-dimensional lattices, they appear from this point of view closer to higher rank lattices than to rank 1 lattices. This raises some questions. Here are the questions which we can ask. So, are these Tralle lattices super rigid in the sense of Margulis? And do they have congruence property, subgroup property? So the answer, as far as I know, to these both questions is not known. So perhaps to ask them to have congruence subgroup property is too much, but well, there is some hope that they are super rigid. If one knows the answer to this question, they will be quite interesting corollaries. So it may quite happen that this super rigid in the classical sense of Margulis, and I don't know. So the hope which we had and we still have that this structure inside with involutions and corresponding FC subspaces would help us somehow to approach these deep questions. Thank you. I think my time is just up.
So in dimension 4, your theorem says that a codimension 1 totally geodesic subspaces are FC, right? But how about the surfaces, just dimension 2? So can you say something about codimension 2?
I guess, well, let me go up there.
Yeah.
So we have the condition, for
Yeah, so I guess I meant yeah, I meant geodesics in this case.
I think so it applies for surfaces. Yeah, so surface you can do weight restriction for geodesics in dimension 4. And I think that my example maybe already applies. Example 1.
Right. So what do you expect? Do you expect some classification of geodesics in this case, or so in general, what happens when this condition on codimension is not satisfied?
Yeah, so I will put a volume up. So can you repeat what is the question?
No. So what happens? So can you? Okay, so your theorem says that all totally geodesic subspaces of codimension at most n+1/2 are FC subspaces. So so what happens if this condition of the codimension is not there? So can you give? Do you have an insight on?
Yeah, we thought about it. So it's possible to use weight restriction of scalars to produce a subspace which is not FC. So it's not only that it's not fixed by involution, it's not fixed by any finite subgroup.
Always, or for every arithmetic?
But yes, but in order to do weight restriction, first of all, you need sufficiently large codimension, so at least like half, because well, you need to this not FC subspace definitely has to be defined on the field of
we can't hear you.
So this is from where the condition on codimension comes, and we first were not sure that it's maybe just technical assumption, but now what we understand is that actually with weight restriction you can produce subspaces which are not fixed by no involution nor any finite sum of commensurate.
Okay, and my other question is about the finite group F. So for each finite subgroups of the commensurator, you have this notion of FC subspace. How does it depend on F? So is there some? So I suppose there are not too many such Fs, right?
So far we only used Fs of order 2. We not produce any interesting example which would require, say, even a product of 2 involutions to define it and could not be defined by a single involution. However, okay, it's just natural to define it for any finite group, and perhaps it could be that we don't see these other Fs in real hyperbolic case, but we can see them in, say, complex hyperbolic case, or even for I don't know, for SLN. So it's natural to define it for any Fs, but so far our Fs were only involutions, so groups of order 2. Thank you.